We're going to look at an example of computing the flux across an oriented surface. So here's a vector field, and the surface we're going to look at is going to be the boundary of a rectangular prism. This is sort of a weird example, but we're going to come back to it in a future video, and that's why. So if we take a rectangular prism, and we're talking about the 6 sides of a rectangular prism, we're talking about 6 different rectangles that are in 3-dimensional space, and those 6 rectangles all together combined will be called S. And so S is closed because it encapsulates a 3-dimensional region that we called E here. And in addition, S is orientable. There's really 2 different sides. You can think of sort of the outside, the part of S which is exposed to the air, and the inside, which is all the stuff that's sort of touching E. So if you think of like a mailing box or something like that, the cardboard that would touch the contents of the box would be the inside. We're going to orient S outward, so all our normal vectors should point outwards away from the rectangular prism, and we will find the flux of the vector field F up here across the surface S. Here's one way that this is written in Stewart calculus. You can replace the D bold S with a bold N, D unbold S. So just keep in mind that ds is equal to nds. No, that's a little tricky as far as wording goes. The surface we're looking at, you could think of as the union of 6 different regions. So this is my attempt to draw the surface, though we're talking about the 6 individual rectangles. So let me highlight like this rectangle in front, and then that rectangle in back, and this rectangle on the right, this rectangle on the left, the rectangle here on top, and the rectangle on bottom. And so to compute the flux, we should just compute really 6 separate flux integrals across each of these 6 individual surfaces, because each of these can be individually parametrized. So if we take a look at the flux through the front, the normal vector should, if you're starting here, should point outward like this, or you follow the direction of the mouse from here out this way. Here's a parameterization, 4 for the x-coordinate, and then u will be the y-coordinate, v will be the z-coordinate. Here's our parameter domain, and if you compute the cross product of ru and rv, you're going to get 1, 0, 0. The plus or minus is to indicate we don't know which one we're going to take for n quite yet, but the thing is, if we want outward this way, then the x-coordinate has to be positive, so we really want n to be 1, 0, 0. So it's sort of a slight misnomer for me to put this plus minus right here, because the cross product really is 1, 0, 0, but had you used switch the roles of u and v, which could have been possible, then you would have, rv cross ru instead, which would have been negative. So you'll see this anomaly show up. I just noticed this in all the subsequent slides. So what's ds? Well, you're supposed to take the norm of this vector, that's 1, and then have a du dv. Okay. F here dot with n here is just going to be 2x times 1 plus, 0 times the other stuff. In the end, once you replace, to get things in terms of u and v, you replace the x here with 4, you're just going to get 8 for f dot n. So the flux through the front is, you do your replacements. Here's your parameter domain, your du dv, and that 8 is for the f dot n, and in the end you get 48. For the surface on the back, the parameterization is a little different. Earlier we had a 4 here, now we have a 0. Otherwise, a lot of this stuff is the same, except now we need the negative vector for the outward normal. From here, you have to have your vector, to orient the surface correctly, the vector should start here and move outward this way, so from here and then moving out that way, but that's going to be a negative x-coordinate vector, so that's why we'll have negative 1, 0, 0. The s is the same. You're going to take this f vector here and dot with this vector right here. I actually have a typo, sorry about that. There should be a -1 right here, but it doesn't matter because we're going to plug in for x right here as 0 anyway, so that's going to be a 0. But sorry, this should read negative 2x, not positive 2x. Oops, but x is 0 anyway, so we're going to get this 0 right here. And when you set up the integral of 0, you just get 0. The integral of for the flux across the surface on the right, parameterized by u for the x-coordinate, v for the z-coordinate, and the y-coordinate is held constant at 3. A lot of the same stuff here, parameter domain. If we want the normal vector out this way, that's from here, starting here, and then moving towards the right, at least from this point of view, that's going to be a positive y coordinate. So we need 0, 1, 0, not 0, negative 1, 0. There's ds, and we're going to dot this vector with this vector and get 10z times 1. The other entries here being 0 and 0 means you don't get this 2x, so that's 6x. And you replace the z here with v from the parameterization, so you get 10v, and you set up the integral and you get something like this. We're not going to compute this integral because of what happens when you look at the flux across the surface here on the left. So basically the same parameterization except with a 0 for the y-coordinate instead of the 3 we had earlier. All that's pretty much the same except the outward normal, just like we saw earlier for the back. Here you need the vector 0, comma, negative 1, comma, 0, so pointing out that way. There's your surface ds piece again. Now when you dot this vector and 0, negative 1, 0, here at least I got this right, this is 10z times negative 1. If you replace the z with v, then you get negative 10v. So you set up the integral for the flux across the surface on the left, and this integral is actually the negative of the integral we just saw earlier, so when you add, these cancel out, which is why we didn't compute. For the top, parameterize as u comma v comma 2 because z is held constant at 2 for the piece on top here. Here's your parameter domain. When you cross the vectors, depending on which order you cross, you get 0, 0, 1 or 0, 0, negative 1, but we need the vector pointing up, so that's 0, 0, 1. Same sort of thing, and you get this integral of 6u du dv, which we won't compute because if you look at the parameterization at the bottom, so replace the 2 that was here before with a 0, and the normal vector is now negative 1 because from here you need a vector to point downward, so that's got to be 0, 0, negative 1. So when you do the dot product of this vector and this vector, you get 6x times a negative 1, so that's, once you replace the x with a u, that's negative 6u, and this integral here cancels nicely with the integral we had just seen for the flux across the top. So in the end, our surface of 6 pieces, which don't overlap except on line segments, the flux across the front was 48, across the back was 0, the left and right cancel each other out. The flux of the top was the same as the negative of the flux on the bottom, so all these are 0 with the exception of this 48 right here.